tau 2, tau 3, tau d. And here we have A0, and we ask, okay, how many complexes can these cells we can construct such that this is bounded by the size of A0.
No, they want to give something much better. I mean, I care about digits, for example, or in general, if you take what the so-called Klee complexes, namely that the complex is completely determined by the one skeleton of it.
Yeah, this is a...
So in such a case, this degree is exactly the degree because, right?
Right.
Yeah, even in Klee complex, or even if it's determined by the I-1 skeleton, then this means that this F is just the number of, there's no additional possible
which means, but this means that when P going to infinity, if I get better, larger and larger complexes, this goes to...
This one will go to 0.
This one goes to 0. So H...
But H can go to... Oh, yeah,
I see. So in a sense, this is like... The fact that it's less than 1 is good and bad.
Yeah.
Depends what you want, right?
Yeah.
If you want to bound lambda, it's better. If you want to the lower one on H, this is worse.
Yes.
It's not better than the conjecture, it's better...
It's better in the sense if you want to bound lambda. If you want to bound H, then it's worse. Yes.
Okay, so this is this inequality is still like along Millman or Tana or this the easy part of the...
Yeah, exactly. And this is what I'm going to prove to you if you want. It took me more time than I expected.
Okay, it's clear that you're going to take the full class. The question now, we in this class have the tradition to take a break. So
sure.
Maybe we should take a break.
There is also inequality, there is some analog of the other direction?
Okay, so let me just give you a few remarks about the other direction, and then we try to generalize it. We had something, but it turned out to be trivial, if you remember correctly. I'm currently working on trying to generalize it. Again, I have some new ideas, but still in progress. I don't want to say anything other than that. Basically, for general complexes, the lower bound is not true. So, for example, if you take X to be this, let's say, size m, then lambda of X is going to 0 when n goes to infinity, but h of X is going to infinity.
Yeah, but this is because this H is this range, it's based on this relative, and there are not so many available triangles at all.
Exactly. Because here we took all the triangles possible, and the skeleton is somehow very...
But this is consistent with the inequality you proved.
Yeah, this is consistent with this one. We are talking about the other direction.
Right, so the generalization,
so
the other direction might include the number of vertices as well.
Yes. So currently there is nothing.
If the skeleton is complete, the dimension skeleton is complete.
We don't know.
Because then
we believe that the lower one is true when, in some sense, when.
But maybe you can improve.
Okay, so the lower one is not going to be as simple as in the graph case anyway, because you can always take this one, the Mobius strip. It's not hard to see that this has a complete skeleton. And here H is positive, I think it's 5/4, but lambda is 0. So no matter...
Why lambda is 0?
Because it's the Mobius strip, it has a non-trivial homology.
Okay, so lambda can be 0 and H can be positive.
Yeah, so what we believe, it's just a conjecture, is that if the skeleton is complete, then there is something of some constant, the degree, minus some other constant, and that this is not going to be trivial, but we can show. So it's just a conjecture, I don't know.
And also here, maybe you can have another definition of H which does not use this all possible, because this is often, this is very restrictive, as you see in this example.
Yeah, I agree.
So it looks that here the expansion should be small.
Here, yeah.
Though it's a one-dimensional expansion. Yeah, it's complicated. Yeah.
H is going
So here we want to find a new, you said that the h of x go to infinity. But we
Yes.
want to understand it so it will not go to infinity, combinatorially.
Yeah.
Yeah. Yeah, so basically there is a big problem with the law. One, we don't know yet how to do it. It's definitely not as trivial, not that the rough case is that trivial, but it's not going to work in the same way. This is a counter example for this thing. And maybe you need to change the definition of the Cheeger constant as well. Okay, so I guess we can take a break and I will give you the proof in the next hour.